remember what our gravimeter accuracy was? 0.001 milligauss. So if we can only measure our elevation to 3 centimeters, which is a lot better than most GPS systems are, we can only get a accuracy or a resolution of gravity of about 0.1 milligauss. So believe it or not, that's about gravity resolution. The free air correction, our knowledge, our ability to measure elevation, is the limiting factor in our ability to resolve gravity phenomena, the accuracy of gravity. Okay, so that's the free air correction. What am I doing when I move gravity from here to here? What am I assuming? Well, basically, I'm assuming that I have air in between, that I have nothing, right? I'm not taking into account that this zone here is rock. So what do I need to do to compensate for that? So if I'm down here now, let's say I move my point of reference. Let's re-look at this. So here I am. Here's sea level. I move my point of reference down to here. And I've done that with a free air correction. So I'm sitting down here, but I've got rock above me. What does that rock do? It exerts a pull of gravity in the opposite direction. So I've corrected the data with the free air corrections, ignoring the presence of that rock above me. Now I have to realize that that rock is there. And this is known, so correct, the free air corrected gravity, and that we'll call it, let's just do it like that for the time being. We have to correct the free air corrected gravity for the mass above sea level right here. So this mass. So we'll call that the correction mass, MC. So first of all, if we do this correction, is this going to be a positive or negative addition to the gravity number? Negative, right. It's going to be negative. Negative correction. And the typical way that we do this is really a half-assed way. All right, this is basically a way that was devised back when we didn't have computers. Sadly enough, we still, in the textbooks, and this is why I'm not changing, because I don't have any better textbooks to explain this. What we do is we actually, rather than considering topography, throw all that out, but we keep our measurement point there. All this is gone, and this distance is still h. And then we assume that there's a uniform slab of height h above us. What a crappy approximation. Okay, but that's what we do. And this assume that it's an infinite slab of thickness h. Oh, and by the way, we assume that the density of this slab is 2.67 grams per cubic centimeter. So we've got two things that we screwed up here already. Number one, we haven't taken in the actual topography into account. Right? Number two, we're assuming a density of 2.67 grams per cubic centimeter in order to apply that correction. So the reason we do that, again, is because we didn't have computers back in the old days. And so this is the Bouguer correction. It turns out that the gravitational pull, and we'll look at this in more detail later on when we look at the pull of the gravitational pull of simple bodies. But it turns out that the pull of an infinite slab is 2 pi g rho h, which is 0.042 roughly rho h in milligauss. So the Bouguer correction, we're going to call this again a Bouguer correction. I'll talk about Bouguer next time. The Bouguer correction is a lot less than the free air correction. It's about an eighth or so of the free air correction. And again, the free air correction is typically added to the observed theta, and the Bouguer correction is pulling up above it, so it's subtracted from the free air correction. Okay, so again, this is now called the Bouguer gravity measurement. In some ways, or sometimes it's called the Bouguer gravity anomaly. So let's go back to this picture now, way back. Hold on, sorry. Right there. Okay. Now incorporate geoid, but also look at Bouguer. Ignore area. So why is the Bouguer anomaly there? Negative. Pardon? Yeah, well, there's not rock above. What we're saying here is that because the geoid is higher, that the pull of gravity is less, which means the Bouguer anomaly will be negative. The pull of gravity will be less than the reference gravity. So the Bouguer anomaly, as you see, always goes opposite to the geoid anomaly. If we're higher, we're further away from the center of the Earth, we have less gravity. And so the gravity anomaly will be negative. Now, why aren't they the same height? I mean, r squared, right? That's the anomaly we're really talking about is r squared. So why aren't they the same height? Kind of a trick question. The geoid is calculated as a potential. Right? It's basically related to 1 over r squared. Whereas the Bouguer anomaly is the force of gravity, or sorry, the geoid is 1 over r. The Bouguer anomaly is actually the gravitational acceleration, or related to this, which is going to be 1 over r squared. Okay. Now, in looking at the relative effects, if you look at the geoid here, and look at the mantle thinning. All right. Now, why is the Bouguer anomaly here more than the mantle thinning anomaly there, and yet the geoid anomaly is less? Why would that be? I mean, shouldn't the relative anomalies be the same? The answer is no. Again, it's because 1 over r versus 1 over r squared. The Bouguer anomaly, because it's 1 over r squared, is sensing stuff, it's sensing density variations nearer to the surface than the geoid is. The geoid is actually averaging or sensing things deeper because it's 1 over r. The acceleration is 1 over r squared, so the acceleration of gravity is going to be more sensitive to things near the surface than a potential. Okay, real briefly, and we'll go back to this next time because the concepts are pretty important. Okay, let's go back to this picture. Let's just say we've got a sea level there. What would be the right way to compute, we've moved this reference